purpose of this lab is to analyze the star's orbital motion in order to find the net force on the star. After analyzing the motion of the star, we are to use its orbital motion to determine the mass of the black hole. The mass of the black hole is to be found by setting the force of gravity equal to the gravitational force equation. Once that is set up, then I'll input my initial values and solve for the mass of the black hole. After running the program, the code spits out multiple masses for the black hole at various positions for the star. In order to get one mass, I calculate the average of all masses to produce an approximate mass of the black hole. Before I can even think about solving for the mass of the black hole, I have to make some changes to my starter code in VPython. First thing I need to do is to change the generic C email and insert my own personal email. Changing that line allows for the program to give me my own unique star trajectory. The values of the star's mass and delta-t needed some rearranging as well to make my code accurate. The star's mass as prompted in instructions is 2 times 10 to the 30th kilograms. The delta-t, which equals 1 day, was given to us in instructions as well. We just have to convert 1 day into seconds, which turns out to be 86,400 seconds. For the rest of the code, it wasn't values we were changing, but instead rewriting the defining equations. As mentioned earlier, the purpose of this lab is to find the net force acting on the star at each position. Since the star is moving in an orbital motion, we can apply what we know about curving motion, which is the net force is directly related to the change in momentum. The change in momentum is broken into two pieces, the change in parallel momentum and the change in perpendicular momentum. The parallel component tells us whether the star is speeding up or slowing down, while the perpendicular component alerts us when the star is changing direction. The parallel component was rewritten and solved by finding the magnitude of the change in momentum and multiplying by the unit vector p hat. With that information, we were able to find the perpendicular component, which is just the change in momentum minus the parallel component of change in momentum. With these new defined lines, we are able to calculate the net force, perpendicular force, and parallel force acting on the star at all positions. Now that we calculate the net force, we can solve for the mass of the black hole. We added 2 new lines of code in order to complete this process. First is the magnitude of the net force. We define that line in VPython. The second new line is the magnitude of distance. Since we knew the black hole was at the origin, we set r to be the distance of the star from the origin and took the magnitude of that. After adding those lines, we are now capable of solving for the mass of the black hole. Once we set our force equal to the gravity equation. After running the program, I received multiple masses for the black hole, and I took the average of the mass to get the black hole's approximate mass of 1.3 e to the 34 kilograms.